Anyway, thank you for the invite. Thank you for the time. I am Felix, and I would love to talk to you about machine assembly with MoveIt. And if you could skip next slide. I would like to make this talk as interesting as possible to everyone watching. And so I decided I would like to first give you a very short introduction about what this project is about me and the company, then describe the system that we're using and that we developed for this, and then go into what we can do with MoveIt, what we did, new features we developed for this, and what's new. And then last, what is still difficult and where there are still things to do. So next, please. So I am Felix, and I focus on making robots do useful stuff. That is my main research topic. And in the video on the right, that's my PhD thesis. I wanted to make robots fold clothes. And as you can see from the fact that 7 Dreamers went bankrupt during my PhD, that is still a very difficult topic. And apart from that, though, I do autonomous assembly, like in this project, and generally task and motion planning, contact-rich tasks, tactile sensing, etc., etc. I work in Omron Sinic X, which is a small think tank of 10, 15 researchers in Tokyo. Omron is a 40,000 people large global electronics company. Next slide, please. And my robotics group focuses mainly on what robots can do when they're soft and compliant. So we have studied learning for soft actuators, making soft robots do useful things, do actual useful tasks, how to teach, how to make them more autonomous, etc., etc. But we're also doing navigation in the wild sort of projects. There's a connection issue, I think. Okay, I think we're back. And also multipolar or multi-agent learning. So this is a very open sort of institute, sort of company. So if you want to do anything together, if you want to collaborate, do get in touch. This is open. Next slide, please. Why are we doing this assembly project? Why are we looking into assembly in general? At the moment, current robot work cells look a lot like this, with a special part-specific jig in the middle and multiple robots doing very specific actions. The idea behind this is to make the whole process that you're trying to develop, in this case it's a kitting process, bin picking and arranging the part in this kit on the right, and focusing or reducing it to very specific small success checks, small binary yes, no, did I manage to go there, divide and conquer like little sub-programs. And this division makes it easy to code and easy to set it up. That's what makes these workflows at the moment possible. But you can easily imagine that if you want to change the part, this is going to be expensive because you have to remake this jig in the middle. And it's not trivial to do that at all. So this is much too expensive. This is not versatile enough. So next slide, please. For the last years, there's been a competition going on, an actual competition sponsored by the Japanese government, the World Robot Summit Assembly Challenge. And the problem that we're tackling in that is exactly this, making robot systems more flexible in terms of assembling drive units like this. The goal is to use all the parts in the top right image in that tray and assemble the drive unit right next to that. In the bottom, you can see the human demonstration of that, and you can see why this is difficult and that there are lots of difficult little parts. You have to, for example, in the left video, hold the shaft and this pulley, then fasten some screws on top of that. You have to align it. You have to make sure that nothing is out of or misaligned. You have to use this flexible part, you have to thread the belt into these two pulleys. Or on the right, this middle idler pulley, you have to assemble multiple parts on top of the screw, then put it through there, add a washer, then add the nut. And if you just use your 2 parallel gripper to do this, you're going to go crazy. Everything will fail. And that's exactly what happened in 2018 when this was first hosted. Only one team managed to do one single unit. We were supposed to do 2 or 3. People can make this or assemble this in 4 to 6 minutes. The target is 15 for the robots. We'll see if we can make it happen this year. Next slide, please. Before I get into what this robot really is, I wanted to mention this is all a team effort. There is an interdisciplinary team from our company, Omron Sinic X, but also Osaka University, ICE Research Institute in Japan, and this year it's Chukyo University who are helping us a lot with the vision. So big shout out to the team. Thanks to all of the students involved, especially. Next. So in 2018, we started, just to give you a little bit of background on why we're designing it this way, with 3 robot arms. One of them had a specific or special little pincer-like gripper that you can see on the top, which we used to grasp parts from the inside, but in the end, that wasn't very helpful. We also had a fixed 3D camera, just like what Ms. Yaran presented earlier, the Zivid camera that was fixed in the scene, and it gave us a very good 3D image, but it turned out to be also not very easy to use because of multiple reasons. First of all, the calibration issues, but also because of reflective parts, etc. So that was our lesson from 2018. That's not ideal either. We did already have the tools that we keep using, and that I'll explain later. And we can, in the video, see that we can fasten screws, fasten these little plates. Next slide, please. In 2020, for this year, the competition is going to happen next month, by the way. It's been delayed by a lot because of Corona. We streamlined the system, and now we're using 2 robot arms with only parallel grippers, simple robotic grippers, and on each arm there's 2 RealSense cameras. So this is a very cheap, except for the UR5E robots, but a very generic sort of robot approach. Anyone could reproduce this. This is sort of a very simple or very standard, like, to me, robot arm setup. In the middle there's the fixation, and we keep using the same tools. So to repeat, 2 arms, easy cameras, standard grippers, and the tools. And these tools, next slide, please. You can see here, these tools you can grasp just like that with the grippers. We're not using complex or expensive tool changers, which are commercial products that we didn't want to buy. We wanted to just use these and be able to arrange the screwdriver, for example, in the gripper if we can't reach or get to a point somewhere. And that has served as well. That is going well enough. We can pick screws from feeders. We can get to places with less than 2-3 millimeter precision, despite there being all of the uncertainty in the grasp, etc. It's quite repeatable. So with the compliance, this also allows us to not have to rely on the impedance control on the robot to apply force. So that's a little bit of a trick that we will come back to more. This is one of the lessons that we learned. Next slide, please. So in these videos, you can see what the robot looks like, or what the system looks like in action. On the bottom left-hand side, you see that we have another tool, this little hook, and it helps us thread the belt. That's demonstrating pretty nicely, in my opinion, how the robot gains in flexibility and gains in functions when you have these sorts of special tools, much like we gain in functions when we hold tools. So we don't only have the screwdrivers, we also have these other things like this hook or plungers or little shovels to do specific things. And on the top right, you see the result of the RealSense point cloud. It's not very good. It's not particularly strong vision, but that is part of the challenge that we wanted to put on ourselves. We wanted to not invest in extremely expensive cameras. We wanted to make this a system that anyone could potentially use, or make this something that a small company could buy and use reasonably, well, have a reasonable chance of acquiring. In the bottom right, this is a bit of a jump forward. You can see that with this caging strategy, it's one of the few things that are a little bit clever and that I recommend that you do if you ever want to do something similar, or that you have a close look at. With that, you can get as far as getting this cable in there. On the top left, you see the effect of the compliance, the screw being gently pushed into the hole, and even some sort of self-correction. Next slide, please. Another thing that we do is we use those wrist cameras to get different views of the scene. And that is something that we wouldn't be able to do with the fixed scene camera. And this is very valuable. In this video, we align the holes of the bearing with the screw holes in the plate. After we pick and insert this bearing, we don't know if the holes match where the holes are supposed to be. So we look at this. Now in the top right, you see where the holes are, where we detected them, then we rotate it a little bit. Here we overshot, and then we turn it back. And this is how we tune the holes. So this is one of the big advantages of wrist cameras. I don't think anyone is surprised, but one should be aware. Next slide, please. Another consequence of the vision system that is quite limited is the precision that we can expect. Every time that we localize a part in the tray, we expect it to be quite a bit off, between 2 to 5 millimeters. So what we do is, like in the left video, we try to center it by grasping it if it's a cylindrical part, or reduce the uncertainty of our estimate of our position estimate as much as possible. And then after doing the centering there, then we can insert the screw tool. And this is a nice example of how compliance helps. Again, because the nut on the back side of this pulley, while we're activating this screwdriver on the right-hand side, we're pushing this foam-loaded, spring-loaded nut tool on the back. And that again saves us all the effort of having to program or having to buy an expensive robot that can do this impedance control. We don't need advanced technology for this one. We just need the right tools. And this tool approach really got us far. Next slide, please. I already alluded to this, but the effect of errors in this assembly task or in this assembly environment is particularly nasty. It's really important that we get our positioning right, or that all of the actions that we take with an object afterwards, they compensate or they take into account how much the part is or could be misaligned. Every time that you grasp an object in the tray, for example, you will get it wrong a little bit. Your estimate will never be perfect, or your robot won't move perfectly to the correct position. But these errors you have to accept. You have to inevitably deal with these positioning errors. And as I said, in the assembly task, this is particularly difficult because the tolerances are very tight. It's less than a millimeter oftentimes, and parts can get stuck. You can miss insertions, you can miss the screw, you can even damage your parts if you're unlucky. You don't want to be going all the way feet forward and blind. That will definitely not go anywhere. Next slide. One of the ways that we propose, can we get to the next slide? Slide 15. One of the ways that we propose to deal with this is object or in-hand pose estimation of the object. After we grasp, we want to confirm where the object is in the grasp. And we can do that, for example, these are two ICRA papers from the last 2 years. We can do that, for example, by touching the environment with the grasped object and then checking which of the positions using the geometry of the scene are feasible. Or we can use the same framework to look at the object with a camera and with a cheap camera even. So this is not difficult or expensive to implement either. This is the current state, but we're also expecting this to, or we're working on this to evolve it. Next slide, please. Because these two are not the only ways that you can use this. We are also using extrinsic manipulation, pushing the object like this. And this is excellent because this also aligns the object to your other objects. If you can arrange it as such, if you can make it happen. If you choose the right approach, if you choose the right method of this and the right moment, you can get around a lot of difficulty and a lot of having to deal with vision or perception issues and simplify the project or the product and the problem that you're encountering a lot. So extrinsic manipulation we're already in the advice section, is something I can strongly recommend if you're ever implementing something like this. Next, please. This is an example. In the top right image, you see that the grasp of the L plate, which is the object that we want to put on the middle or on our base plate now, was not perfect. We didn't grasp it in exactly the right position. We don't really know where we got it, but the sequence of operations that we apply makes it so that the object always ends up in the correct position. It always necessarily drops in this funnel into the right position. So this necessarily succeeds. In the top row, you can see it with 2. On the bottom, you can see that we can also do it with 1 robot only. So this is quite flexible. You can do a lot with this sort of approach. So this is one example. Next slide, please. These sorts of L plates, these large, or these like big objects, they're not the only thing that you can approach this way. There's also cylindrical object like this little screw that if you turn your gripper in the right way, you can end up centering it in your grasp, and then we can do something else with this cylindrical object, like put it into this hole. Next. And lastly, I already alluded to this before. If you use the same sort of extrinsic manipulation approach, using the shape of your grippers to constrain where the object can be, then you can even deal with flexible objects like this cable. Not as perfectly as this without any perception, because you still need to check where this tip is, but you can constrain the rough area where it is quite precisely. Surprisingly, this works quite well. And this simplifies, once again, the problem a lot, because if you had to check the whole area behind this motor, for example, imagine if you just looked at the back and you wanted to know where are the cable tips. I want to grasp them out of thin air. You would go crazy. That's not going to be a simple problem. But if you do it like this, you know that you're already close to the end of the cable, and you only have to look at where the edge or where the tip of it is in front of your gripper. So, next slide. From here on out, it's going to be a little bit more technical stuff, because what we did for MoveIt, or in 2018, what we noticed is that there were obstacles in the way that we wanted to write code in terms of this assembly. All of our assemblies are defined in a way, or they're completely parameterized, rather. They all make an assembly tree, and this tree is defined, for example, by the shaft center being inside the hole of the bearing. But these positions of interest, they were not defined in MoveIt. MoveIt didn't know about it. The planning scene did not know the frames of these collision objects, and that is a feature that we added that is pushed upstream, that is already part of MoveIt now. And the same goes for the pose of an object. It used to be somewhat cumbersome, and it is not anymore. So I recommend that you have a look at this, because this is good stuff now. All of the poses, all of the motions that we define for our assembly are always defined relative to the position of the target or the assembled state of the object. So if we ever change our positions, or if we ever change the size of our objects, everything will change along with it. That makes our approach quite audible. Next, please. Now, this is not something that anyone is going to be surprised by, but since we will release this repository just like we did in 2018, at least for the largest part, I recommend that you have a look at how we structured it and keep it modular as much as possible. For example, there's a database, and we kept each unit separate, and it's all in Python over C++. That's just a little comment, because we don't need the performance in this case. Next, please. One big comment, I don't know who needs to hear this, but ROS has so many amazing visualization and debugging tools, and it would be a sin not to use them. Make sure you get to use them early. There are examples of this too in our repository. You can have a look at what we're doing. We made some AVIS panels and displays. It is very, very strong if you can display what your system knows and intends to do while you're watching it run. You will gain a lot more insight. It will be absolutely worth it. That is a bit of advice. Next. Another feature that you can use in MoveIt is the new MoveIt Task Constructor. I talked about this in more detail at the ROS World 2020 MoveIt session. So if you're interested in this, have a look at that. One comment about this, though, is that this sort of planning is quite expensive. So you don't want to do this online. You do need to take care of how do I save these solutions and then recall them when I need to. That's just a comment. Next. And also the last slide. One feature that's coming up that I don't think is part of other motion planning of say Tesseract, but I'm not sure, is these simultaneous motions. Up until now, it was only possible to move one robot at a time if you wanted to be safe. Now you can safely send multiple execution requests. So you can plan and execute simultaneously and with both of the robot arms independently. On the right video, you see how the both robots independently rearrange the objects that they grasp. And that is, by the way, another neat demonstration of what I talked about when it comes to centering and in-hand pose estimation. On the left-hand side, you can see that the screwdriver works on the bearing there, and the other robot tries to insert the shaft, and they pass quite close. This would never be possible if you wanted to just hope, but it works like this. Yep, you can go to the next 25. So last considerations. There are some things that you will still have to involve or that you will still have to invest a lot of work in, or more work in, if you want to set up a project like this yourself. One is that there's no task creation GUI or anything, and an automatic sequence generation from a CAD model, I think, would make a great business use case. But this is where you have to invest the work. Success checks is something that I mentioned earlier. You need at the moment to have binary success, yes, no gates. And these are at the moment easiest to set up when you have these jigs.